Okay, welcome. Today we are going to talk about partitions, specifically ways to partition a positive integer up into sums of other positive integers. So let's just start maybe kind of in the middle with the number 3. How can we write the number 3? Well, on the one hand, I could write 3 as just 3. So think of that as if you have 3 rocks or something like that, and those rocks are all exactly the same, how many ways are there to divide those rocks up into piles? Well, one thing to do is to put all 3 rocks in just one pile. Also, I could express 3 as 2 plus 1. In other words, make 2 piles of rocks, one pile of size 2 and one pile of size 1. And the only other option is to express 3 as as 1 plus 1 plus 1, and that's just 3 small piles with 1 rock in each pile. I said it already, but I'll just say it again. The idea behind this is that the rocks are indistinguishable from each other. So there's no difference between having 2. It's not like the 3 rocks are all different colors, and so it matters which colored rock is by itself and which is paired with another rock. No, all the rocks are kind of the same. And if you express it in this kind of abstract mathematical way as the number of ways of expressing a positive integer as a sum of other positive integers, then because 1 is just 1 and that's obviously the same as that one, then that issue doesn't arise. But to the extent that this is a counting problem, it's best to think of it as you have a bunch of objects and you can't tell the difference between the objects. Okay, so we can do this with another. Let's just keep on going with and so we have this this number p, and what we say is that p, this lowercase p, of 3 is 3, because given the number 3, there are 3 ways of partitioning the number 3, and built into the old use of the word partition is with respect to sets. So when you partition a set, you split that set up into a bunch of non-empty subsets. Well, here we're partitioning a number, and still the sets are non-empty in the sense that the numbers we're adding are positive. It gets stupid if you were to add it, if you were to allow zeros, then of course there are an infinite number of ways to do it, so that would be dumb. Okay, moving forward, let's just do it with 4. How many ways can you do 4? Well, you can do it as 4, or you can do it as 3 plus 1, or you can write 4 as 2 plus 2, or you can write 4 as, and now we can sort of think of ourselves kind of distributing and breaking up these piles or something like that. This pile of rocks could be 2 plus 1 plus 1, and finally, I think the only way to break it down even more is 1 plus 1 plus 1 plus 1 plus 1. And I think that's just it, by like exhaustive search. Like that's just the only thing out there. And so we say that p of 4 is in fact 5 because there are 5 ways of representing the number 4 like this. Okay, just for completion's sake, we should recognize that 2 can be written either as 2 or as 1 plus 1, and so p of 2 is 2, and that 1 can only be written as 1, and so p of 1 is 1. Alright, so these are called the partition numbers, and they are extremely useful combinatorial objects, and we would like to have some sort of, they are the answer to the question, when we say that p of 4 is 5, 5 is the answer to the question, given 4 rocks, how many ways are there to divide those rocks up into piles? So, have I done something wrong here? I have. Fixed now. Yeah. Good. Okay. Good. What now? Well, what I would now like to do is to explore a sort of strange and powerful technique, which we are going to just touch on only very lightly, but which is an extremely useful and advanced mathematical topic. And that is the topic of generating functions. And what is a generating function? Well, I'm probably not the best person to explain this, but roughly speaking, it's a advanced mathematical technique. It's a function, which is usually a polynomial. I believe maybe always a polynomial, for which when you expand that polynomial out, the coefficients of that polynomial are the answers to some kind of combinatorial problem. And one way of thinking about a generating function is actually just the binomial expansion. So x plus 1 to the n is a kind of a generating function, because it's sort of built into the structure of that polynomial is that when you expand this all out, that you get n choose 0, x to the n, plus n choose 1, x to the n minus 1, etc. And the coefficients of that polynomial are the answers, the binomial coefficients, to some kind of problem you're trying to count. Okay, so keeping that in mind, let's sort of explore, if we can, some sort of weird way in which we could create one of these generating functions. This is going to seem strange at first, maybe because I'm not teaching it well, or maybe because it just is strange. So I'm continuing this line over here. Let's try to explain these partitions. Well, what are our two partitions? We could partition 2 into just itself, and we could partition 2 into 1 plus 1. So, one way to describe that is to say, okay, I have 1, 2, or 2 1s. Okay, so I'm going to write it like that. 1, 2, and I'll just put comma, 2 1s. And notice how I'm sort of just pronouncing almost out loud the quantity of the number first, followed by the number of them. No, followed by the number under discussion. So that's 1. I have 1, 2 is the first one, and then 2 1s is the second one. And so by the way I'm writing this out, if this strange notation is to mean anything, then this notation I'm using must be sort of not commutative in a kind of a certain way. I'm putting a dot here. Don't really think too much about that dot, but maybe you want to think about multiplication, and maybe you don't. Okay, but I'll just mention that this thing I'm considering is in some sense not commutative. Okay, let's keep going, and this will become more clear in a minute. What are other options? Well, here I could do 1, 3. So I have 1, 3, or, and again I'll just put a comma. I can have, well, now I have a mixture of different kinds of numbers, right? So now I have 1, 2, 1, 2, and I'll just write and 1, 1. And then my third option is that I have 3 1s. Okay, that's interesting. Notice that if we interpret this dot as multiplication, then these two multiply to be 3, these two multiply to be 3, these two multiply to be 2, and these two multiply to be 1. And if we somehow treat this ampersand as like addition, then we see that this adds to 3. And in fact, what we observe is that every one of these 3 ways, when expressed in this notation, is in fact a number which adds to 3. Okay, more on that later. Or more on that sort of now. Let's go a little faster now. Here we have 4. So what does that mean? It means I have 1, 4, or, what's my other option? 1, 3, and 1, 1. Another option is I have 2 2s. Another option is I have 1, 2, and 2 1s. So 1, 2, and 2 1s. And my last option is that I have 4 1s. And once again, we see that if we interpret this dot as a kind of multiplication, and we interpret the ampersand as and, then that multiplies to be 4. This multiplies to be 3 plus 1. So this adds to 4, and this also adds to 4, because it's 2 plus 2, that's of course 4, and that's 4 2. And so I'm now starting to kind of feel that something is going on here. Somehow I can count the number of partitions of 4 if I can count every sort of possible combination of numbers written out in this new notation I just invented, for which the sum of those numbers, when interpreted in this particular way, is 4. And what we see is that these things are kind of like acting like exponents in a kind of way. And what I mean by that is these numbers are acting like exponents in the sense that this is what we do with exponents, right? We sort of multiply them and then we add them or something like that. Does that make any sense? Maybe. I will sort of explain. I will now reinterpret this 1 times 4 as z to the 1 times 4. And I will reinterpret this as z to the 1 times 3 times z to the 1 times 1. And I'll interpret this one as z to the 2 times 2. And this as, z to the 1 times 2 times z to the 2 times 1. And this last one is z to the 4 times 1. Okay, what the hell is going on here? What's going on here is that I am sort of building in to I'm forcing these sort of pieces of algebra, so to speak, to perform the computation that I want these numbers to do. And so now, with these strange numbers written out in this form, I've essentially eliminated the ampersand, and now you can fully and truly feel free to interpret this as normal multiplication. And here, because I want these to be added, I just put them in separate exponents, and now by following the exponent rules for polynomials, you multiply and sort of then add. Okay, and so now the problem becomes, okay, if I want to find out the number of ways to partition the number 4, then I somehow need a way to find every single possible product of z's in which the exponents are also some product of numbers, such that however I want to count 1 times 4 and 4 times 1 separately, and then also I'm also treating 1 times 2 and 2 times 1 differently, of course, here. And I want the value of the exponent when computed to be 4. Okay, if this still doesn't make any sense, that's okay. Just hang with me. Hopefully it should be slowly forming some sort of reasonable thing should be happening. Okay, now let's just move on to 5. So how can we do 5? Well, we can express 5 as just 5, or we can express 5 as 4 plus 1, or we can express 5 as 3 plus 2. I like to think of these in terms of, I don't know what example I should use this year. Rocks are kind of boring. In the past I've done puppies. So imagine it's like 101 Dalmatians situation where you have just a lot of puppies, but they're newborn and they're all totally indistinguishable from each other. So they have they look exactly the same. You can't tell one puppy from another. And you have 5 puppies, and then you got some kids, and you're going to give the puppies away to some kids. In the past they were orphans. Let's just roll with that. So we're distributing puppies to orphans, and let's not do orphans. You're gonna just hand out some puppies, and the question is, how many different ways are there to split up the? This example sucks. Let's just go back to rocks. It's more boring.
Babies.
Babies? No, but babies are distinguishable, so it doesn't work. We can do puppies and orphans. The humor of this example doesn't really work when I'm alone in a room. But you want to have some objects which are totally indistinguishable from each other, like puppies. And you want to split those puppies up into different piles. So we're distributing the puppies to the orphans, but the orphans haven't arrived yet. The orphans are coming later in the afternoon, and we're just putting the puppies into piles, man. And so it's damn, we got these 5 puppies. What are we going to do with these puppies? Well, we can just give all 5 puppies to one orphan. Okay, I'm sticking with the example. Or we can give 4 puppies to one orphan and 1 puppy to another orphan. Or you can give 3 puppies to one orphan and 2 puppies to another orphan, etc., etc. Which puppies? Trick question. There's no answer because the puppies are all indistinguishable from each other. So this is just a way of splitting up puppies into piles. Okay, what are the other ways? We could do it as 3 plus 1 plus 1. we can do, that adds to 5. We can do it as, let's see, what's the most reasonable next thing to do? 2 plus 2 plus 1. In class I would make you like do these all yourself. 2 plus 1 plus 1 plus 1. And I guess the only one else is 2 plus 1 plus 1 plus 1 plus 1. No, 1 plus 1. Okay, so I think these numbers all add to 5, and it seems as if there are 7 ways to do this. And so, okay, so first of all, P of 5 is 7, and second of all, it means that there are exactly 7 ways to split 5 indistinguishable objects up into non-empty piles, or just piles. Okay, 7 ways to divide up the 5 puppies. Alright, so skipping right to the sort of algebraic representation, what this means is, and I'm also now going to sort of dispense with the commas and just start writing them as pluses, which is really what's going on here. This is z to the, I have 1, 5, plus z to the, I have 1, 4, and 1, 1, yeah, plus z to the 1, 3, and 1, 2, plus z to the, I have 1, 3, and 2 1s, and so I was right there now I'm here, z to the, I have 2 2s, and 1 1, and z to the, I have 1 2, and I have 3 1s. 3 1s, and finally I just have 5 1s. Note, this should be times. Note that in every 1, 2, and 3 1s. Note that in every one of these terms, the value or the simplified value of each one of these algebraic terms is in fact z to the 5th. If you follow normal exponent rules. And so the answer to this is like 7z to the 5th. And so 7 seems to be, and 7 just is, the answer to my counting problem. Okay, and so now what I want to do is I want to create a generating function which will output as the coefficients of that I want a generating function which, kind of like the binomial coefficients, I want some function that will just crank out, when all is done, a polynomial that I can just look at the coefficients of that polynomial and it will be the answer to this question. Okay, I have a Zoom call in a couple minutes with some of you, so let's try to cram this in before I run out of time. And maybe you'll sort of already see what that polynomial has to be. It has to be, maybe I want to erase the 4 also, we'll see. What I need to do is, I just decided to do this with 6. No, I think I'm just going to, maybe I'll just do it right now. How do I get this, in class I was going to do this with 6 also, but that seems overkill. How do I make some algebra output all these things? And the answer is, let's go. I need every number of the form, so I can have as many as 5 1s. And so what's appearing somewhere here is like 5 1s and 3 1s and 4. Well, that's it actually. But that suggests that I need every number of that form. But I also need there to be up to 1 5. So I need to have 1 5, 1 3. I need all those kinds of numbers. Okay, so here we go. Without further ado, we're just going to do this. Take the following polynomial. I use polynomial very loosely because I don't know what this is. In fact, it is a product of an infinite number of infinite polynomials. The first polynomial is of the form 1 plus z to the 1 times 1 plus z to the 2 times 1 plus z to the 3 times 1 plus z to the 4 times 1 plus z to the 5 times 1. And okay, depending on how you want to think about this, this polynomial, I'll add one more in here, z to the 6 times 1 plus dot dot dot. Okay, so this is take the infinite polynomial of the form 1 plus z to the 1 times 1, z to the 2 times 1, z to the 3, etc. And technically that goes on forever, but if our goal were to answer this question that we already answered, then we could stop here because no larger number can possibly appear. So in practice, if you're trying to compute a particular partition number using a generating function, then the polynomial is not infinite. It's finite and you stop. But technically, if you want to create one generating function which produces the answer to every single partition number, then you take the infinite polynomial. More on that in a second. Okay, and then we keep on going. Now I need to consider, so I've accounted for all the ones, because that's what this kind of means, right? 1, 1, 2 ones, 3 ones, 4 ones, 5 ones, 6 ones. Now I have to count for the twos. Okay, so now this is to be interpreted as multiplication. This is going to be 1 times z to the, I could have 1, 2. It's actually a pretty good explanation. Or I could have 2 twos, or I could have 3 twos, or, and dot dot dot, because this is, once again, an infinite polynomial of the form 1 plus z to the 1 times 2 plus z to the 2 times 2 plus z to the 3 times 2, etc. But in practice, I can't have 3 twos when I'm computing p of 5. So I would stop here if this is all I wanted. But okay, and now you just keep on going, man. You must do this 1 plus z to the 1 times 3 plus z to the 2 times 3 plus this allows for the possibility that you could have 1 3 or 2 3s or anything. You actually can't have 2 3s in this problem. And again, multiplication of 1 plus z to the 1 times 4 plus, and then here we have 1 plus z. This accounts for the idea that you could have some 4s. Here, and now at most you could have a 5. And so dot dot dot, and then we stop basically. Okay, this Zoom call is about to start. I'm just gonna finish this thing though, man. And then if I was doing, I'll just add on one more thing just to indicate the fact that these actually go on forever, and then dot dot dot. Okay, so what is this again? It is a polynomial. If you are okay with polynomials being infinite. This is a product of an infinite number of infinite polynomials. Okay, what's amazing about this product of an infinite number of infinite polynomials is it is a generating function. If you just let this thing go, man, and multiply out this entire thing, what you will find is that, here's the theorem, P of n is the coefficient of z to the n in the generating function that we have just created, in the generating function above. And if you want a more technical, I think you can go in the book if you want. Well, sure. So maybe I'll write one more thing in a second, but before I do, let's just compute, let's just see how this works, right? If you multiply this all out, and I'll now draw a blue line where we stop. If we are trying to compute p of 5 only, then I go from here to here, so that's a polynomial with 6 terms. I multiply it by from here to here, a polynomial of 3 terms. I multiply from here to here, polynomial of 2 terms, from here to here, and from here to here, and then I just stop. So that's going to be a polynomial with 5 times 3 times 2 times 2 times 2. So 8 times 15, big number, 120 terms are going to be in that polynomial. But when you multiply out that entire 120 term polynomial, if I did that correctly, what you're going to get, and I'm not sure I did, what you're going to get is a lot of terms. It can't be that big. Yeah, I guess it is. You're going to get a lot of terms, and when you completely simplify it, what you're going to find is that you're going to have 1 plus some number of, well, I don't know, you're going to get a lot of things. Let's list it in the non-standard order. Some number of z's to the 1s, plus some number of z squared, plus some number of z cubes, plus some number of z to the 4ths, and plus some number of z to the 5ths. And beyond that, this is just going to be some crap, because we specifically truncated our polynomial to only be relevant if I was trying to compute p of 5. And what you will find when you multiply all of these out is that you indeed just get 7 here. And so the coefficient of z to the 5th in the expansion of the product of these things in blue is the answer to the problem, what is p of 5? And okay, last thing, and then I'll go to this Zoom call. The last thing is just to state the theorem. The generating polynomial itself is, another way of putting it is, if you take, actually I'll just stop, that's good enough. Okay, goodbye.